It's that day, the day that every teenager both dreads and anticipates with excitement. All of the questions that have surrounded this mysterious subject, all of the words that we might not understand, all of the mysteries we've wanted to uncover. Well, there are no more mysteries. Today we talk about the periodic table. First of all, I'd like to have you answer this question on the side. What is periodic about the periodic table? So go ahead and answer that, and just do your best. It's not something that we're going to get strict about grading unless, obviously just we want you to put in your best effort. All right, welcome back. So the first question, of course, is why is the periodic table something related to this? Why is it the shape that it is? Why isn't it a shape like this Christmas tree over here, or this word search here in the middle, or even this car? Why do we have that specific design to the periodic table, and is there any background to it? We will be talking about that, but first I want to talk about a theme that you're going to see coming up throughout this presentation. The question is, what is the life goal of every atom? And of course, we answer that right there. The life goal, and if you were to meet an atom, or if you were an atom yourself, your life goal would be to be just like a noble gas. And by that I mean you would have a full valence shell. That's what every atom wants. And you'll see that come up throughout this presentation. You'll see that many of the characteristics of atoms have to do with this principle of wanting to become just like a noble gas. So first of all, and this is related to that topic, we want to take a little bit of a side road and talk about ions. And as, of course, with ions, there are always pluses and minuses. Ions are formed when an atom exchanges electrons with another atom. One atom is giving up electrons, one atom is gaining electrons. And that's how ions are formed. We have both positively charged ions and negatively charged ions. Now, positively charged ions are called cations. That term is right here. I know it looks like cations, but that's not how that is pronounced. You pronounce it cations. And you can remember it here, of course, with this cute little picture here. Cation is an anion with a positive charge, and apparently it is the cutest ion ever. So cations are formed when an atom loses an electron and becomes positively charged. Now, the only clarification there is an atom could lose more than one electron. You could have electrons or ions with 2 positive charges and 3 positive charges. That's fine with cations. They can be not just 1 positive charge, but 2, 3, and even 4 positively charged. Then you also have anions. Anions are formed when an atom gains an electron and becomes negatively charged.
And of course, just like the cations, anions can form a -2 charge, a -3 charge, even a -4 charge. And we'll talk about how to predict some of that on this next slide. All right, what ions are most likely to form? Now, this is interesting. It's something that is not a random thing. I know to this point it seemed like we essentially just say, okay, if an electron gains an electron, or if an atom gains an electron, what charge would it become? Or if it loses an electron, what charge would it become? But what you find by looking at the periodic table, and this is going to go back to the electron configuration information that we learned in the last chapter, you'll be able to predict in many cases what types of ions electrons will form based on where they sit in the periodic table and based on their electron configuration, especially their valence shell. And the theme that it comes back to is the theme that we've already talked about. Every atom wants to be a noble gas. Every atom wants a full valence shell. Okay? And they want to get there with the shortest path possible. Either that might be if they have 1 electron extra from a full valence shell, they might want to lose that electron. On the other hand, if they're 1 electron away from a full valence shell, they're going to want to steal an electron to get to that full valence shell. Let's look at 2 different examples, and then we'll start predicting a few others. Okay, let's look at fluorine first. Okay, fluorine, its electron configuration is, as you're familiar, 1s2, 2s2. Excuse the little marks. For some reason my pen does that, so we're just going to have to ignore those. But 1s2, 2s2, 2p5. Okay. Now a full valence shell, or the same electron configuration as the noble gas, the closest noble gas is neon, that would be 1s2, 2s2, 2p6. Okay. And when we're looking at the valence shell, we're really looking at these last 7 electrons. Okay. The second energy level, a full valence shell would have 8 electrons, and fluorine has 7 electrons. So it's one away from being just like neon. So as you probably have already figured out, fluorine is most likely going to want to steal an electron. It is a very grabby atom, and anytime another atom comes nearby, it's going to want to steal an electron from that atom and become the ion that fluorine would most likely become is F negative. Let me reverse that. So F negative. And F negative, what that means, you just assume that if it doesn't say anything, then it means -1. Okay, so it wants to become a fluorine -1 charge, which means that it has stolen an electron from another atom. Now, when it becomes an F negative, then what has happened now is it has gained 1 extra electron, and now its electron configuration has become, for the valence shell, 2s2, 2p6. All right? And so that happens to be the exact same electron configuration as neon. So that atom has reached its goal in life to become the same electron configuration as neon. Now, I'm sure you can probably figure out already, if we're looking at over here, let's look at potassium. Okay, now potassium has an overall, I'm going to write it here on the left-hand side of the screen here. Potassium has an overall electron configuration of 1s2, 2s2, 2p6. I'm going to continue on the next line. Excuse me, 3s2, 3p6, and then it has 4s1. All right. Now, looking at the valence shell, okay, the valence shell really is just this one electron, okay. This 4s shell, the 4s sublevel in that orbital has just one electron. All right. So the question is, how can potassium get to its life goal of becoming just like a noble gas? Well, the answer is either it could, there's 2 options. Maybe it could gain a whole bunch of electrons and become like krypton. But how many electrons would it have to gain? It'd have to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, well, it would be about 17. It'd have to gain about 17 electrons, and then it would become like krypton. Okay, is that very likely? Not very likely. That would be a very, very strong negative charge for an atom to carry. I don't know if there's ever even a case where you could have an atom with a 17 negative charge or a -17 charge. So no, that is very unlikely. What's the other option? Aha, it could lose 1 electron and become like argon. Okay, it could lose this 1 electron sitting out here, become just like argon. And so that's exactly what it's going to do. The most likely ion for potassium is going to be K+, okay, which of course we assume is a K +1. We just assume there's a 1 there if it doesn't list anything else. All right, and so essentially what happens when it becomes K positive, it's lost this 1 electron right here, and it's left with this as the valence shell, 3s2, 3p6. Which of course is the exact same valence shell as argon. It has achieved its life goal, and so when a potassium comes across a fluorine, that is a perfect match in the sense that these guys are going to definitely want to get together because potassium is very generous. It has an electron that it has no use for, and it wants to give it away essentially. Whereas fluorine is extremely It's a kleptomaniac when it comes to electrons, and it will want to steal that electron. And so potassium holding that electron out there, not really caring what happens to it. Fluorine just very excited to find an electron. They get together, fluorine steals an electron, fluorine becomes F negative, potassium becomes K positive, and now you are going to form what we call an ion. And we'll talk more about that, or an ionic bond. Let me clarify that. We'll talk more about that later. It's going to be KF, meaning that those two come together. The K is a positive and the fluorine is a negative. Now, you'll be able to go through this periodic table and start predicting what atoms become which ions. And at the moment, I'd like you to predict what oxygen would become as an ion, as well as magnesium. Okay, so on the sidebar, predict for me what ion oxygen is most likely to form and what ion magnesium is most likely to form. All right, thanks. Hopefully you were able to answer that. Oxygen, of course, when we look at the electron configuration, I'm going to just do it really quickly. Its electron configuration would be 1s2, 2s2, 2p, check that, 2p4, okay? Now, when we're looking at, again, we really just have to look at the valence shell, which is this part right here. This is in the inner shell. The valence shell is going to be this section right here, which has 6 electrons. And for a full valence shell to become like neon, it would need to have 8 electrons. Okay, so oxygen is most likely going to steal 2 electrons and become O2 negative. All right? And you can also tell that just by, another thing you could do is just look at where it is in the periodic table. It's in group 16. To gain 1 electron would make it like fluorine. To gain 2 electrons would make it like neon. So you just go 1, 2. It's going to form most likely a -2 ion. Okay, magnesium is similar. Just the difference is, of course, it's going the opposite direction. Okay, magnesium, again, it could gain 1, 2, 3, 4, 5, 6 and become like argon, but gaining 6 electrons and becoming a 6 negative ion is honestly pretty unlikely. What's more likely is for it to lose 1, 2. To go, losing 1 would make it like sodium, but it doesn't want to become like sodium. It wants to become like a noble gas, like neon. So it will lose 1, 2 electrons to have a full valence shell. And magnesium then would most likely form a 2 positive Mg2 positive ion. All right, hopefully that makes sense. You can go through and you're going to find that most of these you can predict pretty easily. Like, for example, nitrogen would be a -3. Phosphorus would also be a -3. Sulfur would be a -2. All of the halogens in this row right here, all of these halogens are going to be -1. All of the alkali metals are going to be a +1. Alkaline earth metals are going to be a +2. You can look at ones like aluminum. Aluminum is going to become a +3. And it gets a little bit funny in the middle here, okay? In a few of these, then we have to look at what is the most likely direction, and you'll have to kind of learn that from experience. So we're not going to focus on those too much. Also, when we get into these transition metals, some of these are going to be just a matter of memorization, okay? And we'll go over and show you the ones that you need to memorize, because there are a few. We're just in the conversation of chemistry. For example, you need to know that iron can form 2 different ions. It can form either an iron 2 positive or an iron 3 positive. All right, and those are critically important ions, especially even in the function of the body. When it comes to hemoglobin in the blood, hemoglobin has iron in it, and that's what is critical for carrying oxygen. And iron, it changes from iron 2 positive to iron 3 positive as oxygen attaches to iron, and that's how oxygen is carried in the blood. And that's why blood, if you've ever tasted blood, not that you should go out and taste it, we're not vampires here, but if you've ever tasted it, it does have kind of an iron taste to it, and that's because of the presence of iron in it. All right, now we're going to go over just an overview very briefly of the periodic table. I know that some of the videos you've already seen go over this, so we're not going to go into this in depth. I don't think it's difficult to understand, so that's why we're not going to focus on it too much. Mainly, you just want to know what you need to know, and then go on from there. So what I have here is Mendeleev's periodic table. from the 1860s, and originally he arranged the atoms in based on their molecular weight, molecular mass, and he did a pretty impressive job at kind of aligning elements that had similar chemical properties. And that's one of the first themes you're going to see, is that when you look at the periodic table vertically, because when you look at a vertical column, the valence shell of all of those atoms in the vertical column is going to be very similar, okay, if not exactly the same. And so that's probably the first really critically important theme, is that you want to look at the vertical columns. Now this periodic table, don't get worried about this one, because this one has changed a lot. But it was impressive, you know, that Mendeleev, before we had really a clear concept of the atom and all of these concepts we understand now about the orbitals and about the valence shells, he was still able to put a periodic table together that made a heck of a lot of sense. And a lot of it is still carried over to today. So again, don't memorize this, because this will throw you off. But we look more at it. A couple of things I want you to know. I don't want to, get too extensive here. But here's what you want to know. This, first of all, you have all of these groups here. Group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to group 18. Okay, the groups are columns. Oh, wait, what's going on here? The groups are columns, and in rows are periods. All right, and then there's the key here is really the groups. That's where you start to see similarities in how the elements act. So when we talk about categorizing the periodic table, we're mostly looking at the groups. That's kind of the big thing we're focusing on. For example, probably the one most of you already know, this last group, 18, is called noble gases. They are unique because they are very unreactive. Okay. Now the reason they're unreactive, well, from the previous discussion, you probably already figured that out. They have full valence shells. If they have a full valence shell, they are not going to want to exchange atoms with any other, or exchange electrons with any other atoms. All right. Then we have something here called the halogens. Halogens are very reactive. Okay. They are very hungry to get one extra electron and have that full valence shell. So they are extremely likely to react with other atoms. Okay. The other ones that are important to know, this one over here, way to the left, the first group is called the alkali metals. Okay, now these also are extremely reactive. In fact, they're more reactive, I believe, even than the halogens. Alkali metals are ones that even if you drop them into water, for example, if you put sodium metal into water, it will catch on fire. Okay, they are so excited to give away an electron, they'll give it away very quickly. And whenever they are, usually when you have a chemical reaction, it's going from a less stable state to a more stable state. Whenever you go from a less stable state or a higher energy state to a lower energy or more stable state, you're usually going to have a major release of energy, which in this case comes in the form of fire. So yeah, if you drop potassium into water, it will flame up and burn. Which kind of brings up the question, obviously, sodium is a very reactive metal. And then you say, well, why do we have that in our table salt that we eat all of the time? Well, once it is in table salt, it's no longer neutral sodium. Neutral sodium is very reactive. Table salt, on the other hand, is sodium chloride. Now that electron transfer has already taken place, it's now in a more stable form, and it's not going to hurt us. I mean, at least not in the sense of exploding. Obviously, it can hurt us in the sense of high blood pressure and things like that, but that's more of a long-term effect. But nonetheless, from the standpoint of just exploding, no, it will not explode when you eat table salt. But if you were to eat chlorine and sodium in their natural form and stick those in your mouth, then you would have a major problem. So obviously, avoid doing that. Okay, this next group is called the alkaline earth metals. All right, we don't need to worry too much about the name, but we do know what that is. Okay, these are called, now this is a major theme in the periodic table. Everything to the left, this side is metals. The only exception is going to be hydrogen. Hydrogen is kind of its own game, okay? So even though hydrogen is sitting over on the left-hand side, it is not a metal, okay? And you have to just accept that hydrogen is often an exception to the rules when it comes to the trends in the periodic table. But everything from this, you see this little staircase here, everything from this to this side is metals, okay? Then we have a section here in the middle, and I'm going to put another little outline here just so we can clarify where it is. These in here are called metalloids, and then these are non-metals. All right, and so we'll have a little more discussion about some of these, but I think you know most of what's going on here. I think most of you have seen this. And then we've got down here the lanthanides and the actinides. You can see that name right here. It might be very small on your screen, but lanthanides and actinides, there's not a lot of significance chemically to that. You just need to know where they're located. Those are those inner, this is another word for this, inner transition metals. And I do want you to understand that these really are supposed to go in here. This periodic table should be very wide and would have these two rows stuck in here, and then everything down this line right here would be cut in half and moved out, and then you would insert these two rows. So that's the way the periodic table really should look, but it just wouldn't print very well. And so that's why they have it the way it is, just a reality. So other than that, that's really what you need to know in general terms about the periodic table. I'm not going to, as I mentioned, I'm not going to have you memorize the periodic table. I don't think that is extremely valuable. I want you to know how to use it when you have it in front of you. And we've already talked about how obviously some of the symbols you do need to know, but that was in that Quizlet that we had a few weeks ago. All right, now we move on to the part of the lecture that I think is going to be the most helpful. Okay, we're going to be talking about periodic trends. All right. Now, many of you might be up on style trends. Maybe you might be up on trends of cars, electronics trends. Okay, so you are going to be now learning about periodic trends in the periodic table. So I've got some trendy photos as we go through here, such as this girl over here with this very unique hair. And this is a pretty relevant, trendy look for our discussion, simply because we have these two interesting looking buns that remind me of atomic radius. Okay, so we're going to be talking about the periodic table and how atomic radius changes as you go in different directions across and down the periodic table. Well, first of all, how do we define atomic radius? You guys have all heard the term radius. Of course, a radius is the distance from the center of the circle to the circumference, or to the outside edge of the circle. Okay, and when it comes to atoms, that's a little bit different to define, because when you're looking at an atom, you can't really say exactly where that atom ends. Okay, because you don't really know. We talked about last time how the electron, is 90% of the time in the orbital cloud, but it could be outside of it sometimes, and so it's really hard to say where the atom actually ends. So here's how they define an atomic radius when it comes to atoms. Let's look at the case of oxygen. Okay, it's double bound to itself. It's double bound to another oxygen. This is the type of oxygen that we breathe, this one oxygen bound to the other. All right, and so just so that you kind of understand, these bonds here are represent, let me show you down here. So, and we'll go into what this means, but I'm just going to kind of draw the electrons. So the bonds each represent 2 electrons, okay? And then each of these have 2 more electrons. Oh, let me go back there. Okay, 1, 2, 3, 4. It keeps on switching over there. Okay. Can't get my one more electron in there. It keeps on wanting to switch. I'm just going to put it right there. Okay, so when they're measuring the atomic radius, all they do is they go from, if they have 2 atoms, they find the center of one atom and then measure to the middle of that atom bound to another atom. So the atomic radius would essentially go from right here to right here. Okay, and I've kind of got a funny looking. Let me draw it on this side. Okay, so my pen's doing funny things. But if you can imagine, if you have two atoms bound to each other, let me draw it one more time here. Two atoms bound to each other. The distance from the center of those two atoms to the middle of one of the atoms is the radius. And that's how they define it. Oh boy, I'm having some technical troubles here, as you can see. On the screen here is Alcatraz. Many of you have heard of it. Many of you have probably visited it. Those of you who haven't, I strongly recommend it. Alcatraz was a high-security prison, I believe up until the 1950s. It housed some famous criminals like Al Capone, the Birdman, and some others. So it was quite an interesting spot to visit. But I'm going to tell you a story about it, and the reason for this story is to teach you about atomic radius. All right, I'll kind of give away that connection right off the start. But listen to it carefully, and hopefully this gives you an idea about why atomic radius moves the way it does. So let me tell you the story. So when the prisoners would go out here, this is the yard where they would go out and enjoy the sun for a very short amount of time until they went back to their cells, which were very small and cramped. All right, so when they would go out there, okay, so I'm going to use a negative for a prisoner. And when they would go out there, there would always be one guard that would go out for every one prisoner. All right? And what would happen is the guards would stay in the middle. And as they would watch the prisoners, they would ensure that they didn't stray too far away. All right? So let's just go through this trend here. So on the inside, you had one guard for one prisoner. So when there was two guards and two prisoners, pretty easy to keep people in close. They could easily see them. And then you would start to form this next kind of level. And you can see here, you had about 8. 1, 2, 3, 4. I think we've got 8 now. Then you'd have about 8 of these prisoners around. Let's see here. About 8 of these prisoners around this second level. And of course, every time you added a prisoner, you would also add a guard. So we've got 10. Okay, keep switching on me. All right, so there we go. So now you can see that when we've got 10 guards in the middle and 10 prisoners around the outside, those guards would watch very closely, and that would keep those prisoners in. Okay, but here's what would happen, and this is the key. All right, you would get you'd have this next level then start to form. Okay, I'm going to put this way out here. Okay, now you'd add just one guard and then one electron out here. Here's the key here, or one prisoner, if we keep with our metaphor. The key here is once you get this one prisoner way out here, okay, that prisoner is blocked by all of these prisoners inside these other 2 levels, all right? So even though we added one guard, that guard and these other guards are going to have a hard time seeing this last prisoner. So this last prisoner can stray way, way, way far away, okay? See how I can make this really far away. And it can get a long ways away from the center of that yard, all right? But, so when there's just one out there on his own, it makes it so he can go a very long way away from the middle. Okay, but what happens, though, is as you start adding more of these prisoners, I'm going to erase that one for a second. As you start adding more of them, okay, so now instead of 1, we're getting 1, 2, 3, 4, 5, and we're going to put 1, 2, 3, 4, 5. Okay, as you start adding more prisoners, you're also adding more guards, which will make it then easier. There's going to be more eyeballs in the middle, and it'll make it easier for these guards to see out through the little cracks in these inner shells and essentially pull these electrons in closer, okay? So what happens the point here is this. When you've got one prisoner out there on his own, he can take a very large radius, okay, because the guards have a harder time seeing through the inner prisoners, okay? But as you add more prisoners to that outside shell, you're also adding more guards, or these little pluses, to the middle. And that causes the radius of that group to pull inward and become smaller, okay? And so it's an interesting concept, but as you add more of these prisoners, it pulls that shell inward as you go across. All right, and then obviously what we're talking about here is the atom, okay? But this whole idea of these prisoners in the middle, as you add more of them, being able to see out through those cracks in those inner shells and being able to pull those prisoners in closer is a very similar concept to what you get in the periodic table, okay? Now, if you look at the atom, okay, you have, what happens here is when you have outer electrons, all right, they tend to be pushed out farther because they're repulsed, for one thing, from other electrons, okay? And then the other part is your nucleus here has a harder time reaching out past these inner shells to pull in those outer electrons, okay? So in this case, you can imagine if you've got a shell here with 8, you know, let's imagine we had 8, 1, 2, 3, 4, 5, 6, 7, 8. So if we had 8 electrons there, we had 2 electrons on the inner shell. Then these outer electrons, first of all, they're repulsed by these other negative charges, because we all know that the same charges are going to repulse each other. It's opposites, positives and negatives, that attract, but a negative and a negative is going to push outward, okay? So that's going to be one factor. The negative repulsion here is going to push these electrons out farther. And then the other factor is the nucleus is having a harder time, just like the guards in our previous metaphor, is having a harder time reaching its charge out through these inner shells to pull in these outer electrons, all right? So as you have just 1 or 2 electrons in that outer shell, they're going to take a much wider radius. But as you add more electrons, you're also adding protons in the middle, and that's going to pull that radius in because there's less electron shielding. So here's the two concepts going on. We have something called effective nuclear charge. Effective nuclear charge is the amount of charge that makes it out to this outer shell, because again, some of that charge is kind of blocked, much like those prisoners trying to see those prisoners way out there on the outside. The charge from the nucleus is blocked by these inner shells of electrons. Okay, the next concept is called electron, I shouldn't have called that electron shielding, because that's actually the same thing. The next concept is called electron repulsion. And electron repulsion is this idea that as these electrons come near these inner electrons, those electrons actually have this effect, as shown here, of pushing the electrons out. Let's see what this actually does to our trend on the periodic table. All right, so here is the trend. I'm going to give you the overview. It's a little bit counterintuitive initially, all right? So here's what it is. Your atomic radius is going to increase. I'm going to always, with these arrows, I'm going to always put the arrow pointing in the direction of increasing. Increasing atomic radius. And then also this way too. Increasing, sorry about the sloppy handwriting. All right. Now, what these arrows mean is that as you move to the left on the periodic table, you get a larger atomic radius. Okay? That is the part that's probably the most tricky to understand, because lithium has only 3 electrons. Beryllium has 4 electrons. Now, initially, when you hear that, you would probably think, wait a second, if beryllium has 4 electrons and lithium has 3, then beryllium must have a larger radius. Wrong. Okay? It doesn't. You have to think about it much like that metaphor I was telling you. Every time you add an electron, you also add a proton. And much like those prison guards, they're then able to, the protons are like prison guards, they're then able to see out through that inner shell to those outer electrons better, and they will pull those electrons in better. Whereas in the case of lithium, you only have one electron sort of sitting out there in its own shell, and it will have a large area for it to sort of stray in. Okay? So, and then as you go across here, every time you go one more atom over, you're adding both a proton and an electron. But the electron is only being added to the same shell. Okay, so those prisoners the guards in the middle then are able to, or protons, then are able to more easily see the prisoners or electrons that are in that same shell, and they're able to pull that shell in. Okay, so here's the key. Lithium has a larger radius than beryllium. Beryllium has larger radius than as we go along here, it's going to have a larger radius than oxygen. And oxygen is going to have a larger radius than fluorine, and fluorine is going to have a larger radius than neon. Okay, then let me just clarify here. Then we jump down here to sodium. Okay, now sodium, the trend totally changes because now we've moved down one. Okay, now we have one extra shell. We have one electron sitting in its own shell on the outside. Okay, and that electron is going to stray very far, and that atomic radius is going to get larger. Okay, and then as you go across again, it will get smaller. All right, so here's the key. Now look at these arrows. Again, as we move to the left, the radius gets bigger. So fluorine has a smaller radius than oxygen. Oxygen has a smaller radius than nitrogen. Okay, now there's going to be some minor exceptions in here. Okay, I'll tell you that right off. But in general, as I move to the left, the atomic radius gets larger. And as I move down the periodic table, the atomic radius also gets larger. Now that makes sense. I think everybody understands that as you add extra shells, those shells are taking up more space, and you're going to get a larger atomic radius. So the vertical trend is, I think, a pretty easy one. The horizontal trend when it comes to atomic radius is a little bit counterintuitive. Okay, so here's what I want you to do. On the side of the screen here, answer a couple of questions about which atoms have larger atomic radii than other atoms. All right, welcome back. Hopefully those went well. I'm going to compare a couple here. These actually might be different than the ones you looked at. Let's do about here between fluorine and nitrogen. Okay, so fluorine and nitrogen, fluorine is going to have, now if you look at this trend, as you move to the left on the periodic table when you're on the same row, you're going to get larger in atomic radius. Therefore, nitrogen is a larger atomic radius than fluorine. Okay, that's of course when we're only talking about atomic radius. Okay, now let's look at another two here. Let's look at lithium and sodium. Lithium and sodium. Now this goes to this vertical trend here. As you go down the periodic table, the radius increases. So lithium, let's put it the other way around. Sodium has a larger atomic radius than lithium. All right, and then we can compare these as we go across. There's a whole bunch of comparisons that we can make. We could look at oxygen and sulfur. Of course, sulfur has a larger atomic radius than oxygen. And then let's look at phosphorus and magnesium. Okay, we look at this trend up here, this arrow. All right, magnesium is going to have a larger atomic radius than phosphorus. All right. Okay, so hopefully that makes sense. And you'll want to practice it. As you practice it, you'll get it down because you will get these mixed up initially. The next concept is called electronegativity. What electronegativity is it is the amount of pull that an atom has on electrons. Okay, this goes back to that same concept with the same theme that we said would come up over and over again, and that is that every atom wants to become like the noble gases. Okay, so the closer it is to becoming like a noble gas, if it really wants electrons to become like a noble gas, it is going to have a high electronegativity. Okay, that's what that means, is electronegativity refers to how strongly an atom pulls on electrons, essentially, or grabs on an extra electron, all right? And so, on the other hand, if it is a case like lithium, okay, which has only one electron in its outer shell, that is not going to want an extra electron very much. In fact, very little at all. So that would have a very low electronegativity. Okay, we'll look at this in more detail here. Here is kind of a definition. Electronegativity is the ability of an atom to attract electrons when in a compound. Here's the key here, is we are talking about, again, sorry about the little ink things there, we are talking about when the atom is in a compound. So you want to think about this. I think this picture here really sums this up well. If this bottle represents an electron, okay, you would have these two atoms, all right? And the question is, which of these is more electronegative? Okay, now as it looks like to me, I would call this one more electronegative. Okay, so this baby, or this atom, is more electronegative because you can see that as these two fight over an electron, it seems that this baby has pulled this electron closer to it. Okay, that would make it more electronegative. Okay, so when atoms are sharing electrons, whichever one pulls that electron closer to its side is the most electronegative. Okay, so essentially, as I say here, electronegativity is how selfish an atom is when it comes to sharing. Okay, the atom that pulls the electron to its side is the most electronegative. Let's look at the trends here. All right, so I'm going to draw my arrows up here. Okay, so as we go in this direction across the periodic table, we have more electronegative. And as we go from the bottom to the top, then we have more electronegative. So on this periodic table, the most electronegative atom is going to be fluorine. All right. Now, I'm going to tell you this right now. When we talk about electronegativity, we ignore this row. Okay. We don't really include the noble gases at all. Okay, we just leave those out of the discussion, and you'll see why. There's a very good reason why. Obviously, they've already got a full valence shell, so they really are not trying to attract extra electrons. So they really just aren't factored in, and they also don't bond with other atoms, and so we just don't really talk about them when it comes to electronegativity. But fluorine would be the most electronegative, and as we go in this direction, essentially, we are becoming more electronegative. Yep, we kind of messed up our writing there. I'm going to just kind of write over it so I don't have to pull out the eraser. Boy, that was a really bad word there when I spelled that out. Anyway, you get the point. Okay, so fluorine is the most electronegative. Francium would be the least. Let's try it again this time. Negative. All right. So we can start comparing here based on these arrows. Okay, so if we compare oxygen and fluorine, which one is most electronegative? Well, we could think about this in two ways. We can just look at our arrows for one, but we can also consider the fact that fluorine is one electron away from being like neon. All right. So fluorine really wants an extra electron. Oxygen then is two electrons away. Okay, it's a little bit, it doesn't have quite as much hope as fluorine has. Fluorine is almost there. It's very, very desperate for one extra electron. Oxygen, on the other hand, is kind of like, okay, I'm almost going to have to, maybe have to live with this a little bit more. Yeah, it also wants two electrons. It also wants electrons, but not quite as badly as fluorine, because fluorine is so close to being like a noble gas. And so oxygen is going to be a little bit less electronegative than fluorine, okay? Nitrogen will be a little bit less than oxygen. Sulfur is less than oxygen, okay? Now, sulfur, the reason that it is The reason that it is slightly less electronegative than oxygen is because oxygen's outer shell is closer to the nucleus. Okay, so while it is searching for extra electrons, the shell is closer to the nucleus, which means there will be a stronger effective charge coming from the nucleus. So a stronger ability to pull in extra electrons, whereas sulfur has an extra shell. That outer shell is a little bit farther away from the nucleus, so the effective charge from the nucleus is not going to be quite as strong in this case of sulfur to pull in extra electrons. All right, so we can start comparing these, and I want you to do that now. Let me just compare two more just to give you a sense. So if we compare phosphorus versus silicon, which is more electronegative? Well, let's just look at this trend here. It's more electronegative as you go to the right. So phosphorus is more electronegative than silicon. I think I said sulfur, so if I did, I apologize, but that is silicon. We could compare, let's just look at these two also, magnesium and sodium. Now, these are a comparison of the light weights when it comes to electronegativity. Okay, neither magnesium nor sodium is very electronegative. But when we look at this trend here, magnesium, if we're talking about gaining electrons, magnesium is going to, one electron is going to get it closer to a noble gas than sodium, because magnesium, one electron would get it within 5 electrons of a noble gas, whereas sodium gaining an electron would only get it within 6 electrons of a noble gas. So in this case, as we look at our arrow as well, magnesium would be more electronegative than sodium. Okay, I've got a couple of practice problems on the right-hand side. Please try those and see if you've got electronegativity figured out. All right, welcome back. Hopefully those went well for you, and we're going to now move on to the next concept. Okay. The next concept is first ionization energy. And of course, since we're talking about trendy hairdos and trends that we come across, I have a picture of a kid with his hair sticking up. That is a very relevant picture because when you have an ion, one of the effects can be your hair can stick up. When you rub a balloon, for example, against your hair, what you're doing is you're removing electrons. You're moving them from your hair to the balloon. And then when you bring the balloon close to your hair, it'll cause your hair to stick up. And so that really, we're talking about ions, okay? So when we're talking about first ionization energy, here's the key definition here. First ionization energy is the energy required to remove the first electron from an atom, okay? So here's how you want to think about this. The more an atom wants an electron, the harder it is to take it. The less an atom wants an electron, the easier it is to take it. So we need to look at the periodic table and decide which of these atoms wants electrons the most and which wants them the least. So again, first ionization energy is the amount of energy required to take an electron from an atom. If we compare, let's just compare lithium to fluorine. Which of these two would be easier to take an electron from? Okay. Obviously, it's going to be easier to take it from lithium because lithium has that one electron in its outer shell, and lithium wants to become like a noble gas, just like fluorine does. But lithium is going to be able to give up an electron and become like helium. So it's not even, it's not even holding on to that electron very strongly. It's going to give it up quite easily, okay? So lithium has a low first ionization energy, meaning it doesn't require much energy to take an electron from lithium, all right? It's kind of, it's hanging around, but it's not really holding on to it very tight. And then somebody comes along, they take it, it's like, hey, that's fine. I'm just like helium. That's my goal anyway. Fluorine, on the other hand, is one electron away from being like neon. All right, it really wants an extra electron. That also means that it's really going to hold on very tightly to the electrons it already has. Okay, so fluorine then would have a very high first ionization energy. So it would require a whole bunch of energy to take an electron from fluorine. Here's the trend. Okay, as you go horizontally across the periodic table, you have increasing first ionization energy. Also, as you move up the periodic table from the bottom, you also have increasing, I'm just going to put ionization energy. Okay, boy, that's sloppy writing. Sorry about that. I'll have to work on that. Okay, so let me just put let's at least get our trend straight, though. I'm going to erase this really quickly and get that a little bit better. Let's get our trend clear. So, here we go. All right. So as we go up the periodic table, we have increasing ionization energy. Now, I already talked about the horizontal trend. Okay, and I think you understand that. Now, when we talk about the vertical trend, all right, again, the harder it is to remove an electron, the higher the ionization energy. Okay, so here we have the case where as you get lower on the periodic table, the outer shell becomes farther away from the nucleus. That means the nucleus is exerting less force on those outer electrons to pull them in. Okay, you go back to our idea, our metaphor around Alcatraz. So as these get farther away, they have less of a pull from the nucleus, and it becomes easier to snatch them away. So in our metaphor about Alcatraz, these ones that are farther away from the nucleus are the ones that could easily be picked up by a boat coming along. Okay. Whereas as you get closer to the shell, closer to the nucleus, the pull of that center is going to be stronger. In other words, when we have a guard there, they're going to be able to keep close watch on those electrons. So as you get closer to the nucleus, it becomes harder to take those electrons away. So potassium is going to be, it's going to be easier to remove the first electron from potassium than it will be from lithium. Okay, it'll be easier to remove the first electron from iodine than it will be from chlorine. Okay, even though none of these are easy anyway, because these are in that 17th group, which is one away from being a full valence shell, or like the noble gases. Okay, so go ahead on the side and try some of these comparisons to see if you've got down the first ionization energy. See if you've got that figured out. All right, welcome back. Hopefully that went well for you. And I want to show you just one more thing, and this will be the last slide in our... Oh, wait, we got 2 more slides. Okay, I want to just show you one more thing on this. This shows this ionization energy, how it proceeds. This chart will look very confusing initially, but essentially it'll make some sense when you think about the way the shells work, okay? So first of all, hydrogen and helium. Helium, it's extremely hard to remove an electron from, okay? And so that would have the highest first ionization energy. Okay, but then we get down here to lithium. Lithium only has 1 valence shell electron, so it's very easy to remove an electron from. Okay, but then as we go through this trend, now there are some little exceptions in this trend, like beryllium and boron. Okay, and I think you'll figure out that when you think about the S and the P shells, you'll figure out why it has these. Also, there's another little switch here that has to do with Hund's rule about the fact that when it's half full, it has more stability than when it has just 1 electron there. Okay, so interestingly, all that work that we put into understanding electron configuration is going to help you understanding trends like this. But the overall trend as you move from lithium all the way to neon, fluorine and neon, is the ionization energy increases as you go across that period. Then all of a sudden, the ionization energy drops dramatically down to sodium. Sodium has only 1 valence shell electron, and that means that that electron is shielded by the other electrons. It has less effective nuclear charge, and there's also that repulsion going on, which means that outside electron is very easy to remove. Okay, as you can see. Then as you move all the way to argon, that gets harder, then it drops down again. Okay, so you can see the way this trend works. I know if you study this, and I would actually recommend you put this on pause for a second and just study this chart for a second and make sure you kind of understand these trends when it talks about this ionization energy and the amount of the difficulty it is to remove one electron from each of these atoms. Okay, this final slide just summarizes everything. And I put X's through 2 of the arrows only because you don't need to worry about these 2 right now. The electron affinity is something that essentially you can just think about it as meaning the same thing as electronegativity. Okay, so electron affinity and electronegativity are essentially the same thing. There is a distinction, okay, so I'm not going to tell you that they're exactly the same thing, but the trends are the same and the concept is very similar. Okay, so you don't need to worry about that one. But everything else on here you should understand. Okay, ionization energy, electronegativity, atomic radius, and this also includes metallic character and non-metallic character. So you know that in the top right you have atoms that or elements that are less metallic and they're non-metals. And then as you go down and to the left, you have more metallic character. And then of course you have this spot down the center here that we talked about, and we'll go over which ones we're referring to in a separate slide, but those would be the metalloids, okay, or the semi-metals that have some characteristics of nonmetals and some characteristics of metals. So on the side here, I want you to answer just a couple of questions that just summarize this whole periodic table, and hopefully you've got it all down. If you don't, come in and talk to me during any tutorial, and we will get these down. A little practice and they will be no difficulty at all. Thanks a bunch. Talk to you later.